Hi. In this video I will introduce the concept of total internal reflection and critical angles, and we'll also have a look at optical fibres. In my previous video I explained refraction and Snell's law, and we noted that light passing from one medium to another medium partially reflects back and partially refracts. When light is moving from a high refractive index to a lower refractive index, for example here from glass into air, it bends away from the normal, so the angle of incidence is smaller than the angle of refraction. What happens if we keep increasing the angle of incidence? The angle of refraction is getting closer and closer to 90 degrees. Eventually, beyond a certain incident angle, the angle of refraction hits 90 degrees. We call this incident angle the critical angle. And for this glass-air boundary, the critical angle is around about 41.8 degrees. If we increase our incident angle beyond the critical angle, notice what happens. There is no more refraction. All of the light is reflected back inside the glass block. None of it escapes into the air. This is called total internal reflection. In my previous video I explained Snell's law, but let's apply Snell's law to calculate the critical angle for light at a glass-air boundary. Well, θ1 here, the incident angle, is our critical angle, so let's call that θc. θ2, at the critical angle, by definition θ2 is exactly 90 degrees. This is the point where the ray of light skims along the boundary between the two media. So we can substitute these into Snell's law to give us n1 sine θc is equal to n2 sine 90, and sine 90 equals 1, so we can say that sine θc, the sine of the critical angle, is equal to n2 divided by n1. If we substitute in the values for our glass-air boundary, where n1 is glass, which has a refractive index of around about 1.5, and n2 the refractive index of air, which is approximately 1. So n2 over n1 will be 1 divided by 1.5, which is 0.67. So this gives us a critical angle θc equal to 41.8 degrees, which agrees with the simulation that we saw earlier. This means that any light shone at a glass-air boundary at an angle of greater than 41.8 degrees from the normal will undergo total internal reflection. What if we swapped the glass and the air around? What's the critical angle for light going from air into glass? Well, that would be θc is equal to sine to the minus 1 of 1.5 divided by 1. Now some of you might have already noticed a problem there. If we put that into a calculator, you'll get an error because you can't have a sine greater than 1. Mathematically that doesn't work, but also the physics don't work either. When moving from a low refractive index to a high refractive index, light bends towards the normal, so there is no incident angle that would ever cause the angle of refraction to exceed 90 degrees. So that means there are two conditions for total internal reflection. Firstly, we must be going from a high refractive index to a low refractive index, and secondly, the angle of incidence, θ1, must be greater than the critical angle, θc, where sine θc is equal to n2 divided by n1. Total internal reflection is essential for much of our modern world. It is the theory that allows optical fibres to be used to transmit data around the world. Pulses of light are sent down an optical fibre, usually to transmit data signals for the internet or cable television. As long as these light rays hit the boundary above the critical angle, by entering through what is known as the acceptance cone, total internal reflection will occur and the rays will continue along the fibre. An optical fibre consists of a central core through which the light rays travel, surrounded by cladding. Both are made from very pure glass, but the core will always have a higher refractive index than the cladding. This ensures a consistent critical angle throughout the fibre. Optical fibres have a few advantages over the copper cables that could otherwise carry data. Firstly, they can carry multiple signals down a single strand at the same time. Secondly, they don't lose much energy, whereas the current in copper cables causes them to heat up, which is a waste of energy. And number three, they're actually more secure, because if somebody cut an optical fibre to listen into the signal, that would break the flow of the signal and the break would be detected by the receiver. But there are some challenges faced by optical fibres. Firstly, there's attenuation. Some of the light is going to be absorbed by the glass, and that will cause the signal's intensity to decrease as it travels along the optical fibre. The solution to this is to just use much more pure glass, which will not attenuate the signal as much. The second issue is modal dispersion. So if we made an optical fibre with a wide core, some of the rays of light will travel a much greater distance than others, because some rays of light will come in at a sharp angle and reflect more than the ones travelling at a shallow angle. This means that the two rays of light will arrive at different times, resulting in a signal that is out of sync. The solution to this is to not use a very wide core. We should use as narrow a core as we possibly can. And the final problem is something called spectral dispersion. If we shine white light down an optical fibre, the different frequencies within that white light are going to refract differently due to having different refractive indices. This is going to cause the light to disperse like a rainbow, smudging the signal again. The solution here is to use a monochromatic light source. In other words, a light source made of a single frequency of radiation. Most commonly, this is actually infrared radiation.